Hello everyone, this is Andrea from Yellow Academy and Brain Boosters, and today we are going to see chapter 18. This is paging introduction, and let's get into it. So as you can see, what is the concept of paging? And as you can see, paging splits a virtual address space into fixed size unit called a page. And most of the time the page size is 4 kilobytes or 4096 bytes. And segmentation, we have another technique, we have seen it in chapter 17. This one is a variable size of logical segment. We have a segment for the code, we have a segment for the stack and heap and etc. It's not fixed. So with paging, physical memory is also split into some number of pages called a page frame. So whenever you see a virtual address, we have a page, and whenever you see a physical memory, we have a page frame. So the difference between paging and segmentation is in the paging we have equal fixed size of 4 kilobytes most of the time, but in segmentation, as you can see, we have different size for the code, for the stack and for the heap. And we have also another concept of page table for process is needed to translate the virtual address into physical address. So whenever we have a virtual address, and it should be translated into physical address, and all the information about this will be stored in the page table. The advantage of page table paging is first, it is flexibility, supporting the abstraction of address space effectively. Don't need assumption how heap and stack grow and are used because it is fixed size, as we have seen. Simplicity, ease of free space management. The paging, the address space and the paging, the page frame are the same in the physical memory and in the virtual memory, they are the same. Easy to allocate and keep a free list as well. So let's see an example here. We have 128 bytes of physical memory with 16 byte page framing, as you can see in the right, and in the left we have 64 bytes of address space with 16 bytes of paging. So we have this. So if we were trying to map the virtual memory into the physical memory, what we have to do is page 0, as you can see here, will come mapped into page frame of 3. And page 1 is mapped into page frame of 7, and page 2 is mapped into page frame of 5, and page 3 is mapped into page frame of 2. So this one is the address space of the running program, and this is how it mapped into the physical memory. And if we had to construct the page table, as you can see, we have the page table here, and we have the physical, the page frame. Okay, so as you can see, 0 is mapped into the page frame of 3, 1 is mapped into the page frame of 7, 2 is mapped into the page frame of 5, and 3 is mapped to the page frame of 2. So address translation, how we gonna translate the address? Two components in the virtual address are here. As you can see, we have VPN, virtual page number, and we have offset within the page. So we have VPN and we have offset. So we have the lowermost bytes here and we have the uppermost bytes here. So these 2 bytes will tell us the VPN and the other is the offset. Let us say we have 6 bytes of virtual address space, as you can see, 0, 1, 2, 3, 4 and 5. So this is how the translation is done. From VPN it will be translated into the page frame of physical page frame. So let's see an example. We have the virtual address of 21 in the 64 byte address space. So in binary, 21 is 010101. So if you put in the 6 byte address space 010101, so 0 and 1 will be the virtual page number, and the offset will be the rest. So the virtual address 21 in 64 byte address space, we have the virtual page number 0 and 1, then it will be translated into address translator. Through address translator, it will be translated into physical address and this will be page frame number, PFN. So this is how the translation. So the other question is, where are page tables stored? Page tables map the virtual page number, VPN, to the physical page frame number. So this is the idea. And page table can get awfully large. 32 byte address space with 4 kilobyte page, 20 bits for VPN is required. As you can see, 4 megabytes to the power of 20 entries. This times 4 byte per page table entry. Then we need 4 megabytes. Page table for each process are stored in the main memory, and one page table for each process. Example, given a 32 byte address space with 4 kilobyte page, 20 bits will be used for VPN and 12 bits for offset. Assume 4 bytes will be used to store an entry in the page table, and 4 byte page table per process is required. So this is one of the downside of the page table. So if you will see the operating system in the kernel physical memory, as you can see, the page table will show us 3752. This 3752 is the page table we have constructed here, 3752. This is the frame, the page frame number. And the virtual address is marked already. And this will be in the operating system. And this is the physical memory. So we have page 3, page 0, page 2, page 1. And they are mapped into the page frame of the physical memory. What is in the page table? The page table is just a data structure that is used to map the virtual address to physical address. Simple form, a linear page table in the array. The operating system indexes the array or the page table by VPN, virtual page number, and looks up the page table entry. That is how it works. Common flags of page table entries. For example, we have valid bit. This indicating whether the particular translation is valid or not. Protection bit, indicating whether the page could be read from, written to, or executed from. Present bit, indicating whether this page is in the physical memory or in the disk swapped out. Dirty bit, indicating whether the page has been modified since it was brought into memory. Reference bit, access bit, indicating that the page has been accessed. So let's see in the x86 operating system page table entry. So we have 32 bit, as you can see, from 0 to 31. So we have the page frame number, and the page frame number took from 12 until 31, and we have void here from 9 to 12, and the other bits are here. So in the x86 page table entry, P represents the present, RW represent read or write bit, U/S represent supervisor, A represent access bit, D represent dirty bit, PFN represent the page frame number as you can see here. So paging is too slow. Why? To find the location of the desired PTN, page table entry stored in the main memory, the starting location of the page table is needed. For every memory reference, paging requires the operating system to perform one extra memory reference. Address of the start of the page table is stored in the page table base register. So this is page table base register. This is a register type of register. The address of the start of the page table is stored. This is a simple code accessing memory with paging. So what it does is, the first one is extract the VPN from the virtual address. So we have VPN. So we have the virtual address, and this will be end VPN mask, and it will shift it by 4, the value of 4. So VPN mask, to mask the VPN, let's say 21, this is our binary 010101. So the VPN mask will be 110000. Then as you can see, we will get, then the shift will be 4, and we will get 00010. This will be the VPN. From the address of the page table entry, we're gonna find PTBR. PTBR means here page table base register, then page table page register plus VPN times size of the PTN will be this code, page table entry. This will give us the PTE address. Then fetch the PTE, the page table entry. PTE will be access memory. So this will be fetched. Check if the process can access the page. Then we have if clause here. PTE valid. If it is false, raise exception, segmentation fault. Else, if can access PTE protected byte, false, raise exception. Else, access is okay for physical address and fetch it. The offset is equal to the virtual address and offset mask. What is offset mask? Offset mask 21 changed into binary 010001. Again, the offset mask 00111. Then we have 0101. So once we get that, physical address is equal to PTE, the page table entry. Then we have the PFN. Then this should be less than PFN shift offset. Then register is equal to access memory physical address. So in this way, this simple code work. And the memory trace example, a simple memory access. This is also taken from the textbook, and integer array 1000 for I is equal to 0, I less than 1000, and this is the increment array from I is equal to 0. So if we compile and execute this code, use this code gcc -0 array.c, this is a C language, and wall and pop, then we have the array. Then resulting assembly code will be, looks like we have the register number, the increment, and the compare, and we have the jump, so the location also here. So a memory trace, some assumptions to explain the code. Let's assume a virtual address space size of 64 kilobytes and the page size is 1 kilobyte, and linear page table array is located at the physical address of 1 kilobyte. This is 1024. Then the content of the page table will be, the code assumes virtual VPN page number 1 mapped into PFN4. Then we have the array. The array, we have 4000 bytes because we have 1000 times 4, 4000 bytes, and the size of it. Then assume at a virtual address of 40,000 to 44,000. Then this will be how it mapped. VPN 39 will be mapped into PFN 7, VPN 40 mapped into PFN 8, and VPN 41 mapped into PFN 9, and VPN 42 mapped into PFN 10. So this is how the mapping done. And the virtual and the physical memory trace for the first 5 iterations will be, it looks like this. The most important thing is each instruction fetch generate 2 memory. The first one is 1 to the page table and B another to the actual location of the instruction. The move instruction will also require 2 memory references. The first one is 1 to page table and the other one is to the array element itself. So these are the issue. So as you can see, page table 39, and we have page table 1, and we have the array, and in this direction, as you can see, the virtual address in the left direction, and we have the physical address in the right direction. In this way, that is the end of chapter 18. I hope it was helpful. I would like to thank you for your time, and we will come with another chapter. Thank you. This is Engineer's class. Bye bye.